Hello everyone, it's Mr. N here again, and this time we are going to do the Chapter 6 additional review that you guys got in class, so let's go ahead and go through this. On the first one, we've got, it's given that f of x equals the square root of x minus 1, and we need to find a value c such that f of c is the average value on this interval from 1 to 10. So looking at this, from 1 to 10, we have an average value function that we have to find, but we have to find this value of c on our average value function. So let's go ahead and set this up. We know the average value is 1 over b minus a, the integral of from a to b of f of x dx, which is our function. In this case, our function is f of x equals the square root of x minus 1, and our interval from a to b is 1 to 10. So 1 over 10 minus 1 from 1 to 10 of the square root of x minus 1 dx. Now, we need to find this value c in f of c, which means this has to equal our f of c. That's how we set these up, and our f of c is just going to be this c minus, the square root of this c minus 1 when we plug c into our f of x equation. So that means I'm trying to find this value c that will be the average value here. So let's set this up and integrate. We end up with 1/9, and this ends up being the integral. This will end up being 2/3, and this will be x minus 1 to the 1/2 plus 1. So this will be 3/2 power on the bounds from 1 to 10. And we can go ahead and solve this. We end up with 2/27, so I'm going to take this out. And then this will be 9 to the 3/2 minus 0, which ends up being 2. So we set 2 equal to the square root of c minus 1 value, and then we get 4 equals c minus 1. c is going to end up being 5. Okay, for number 2, this is very similar. Given f of x equals x squared, find the average value c such that f of c is the average value on 0 to 6. So, similar problem. We end up with 1 over 6 minus 0 on the integral from 0 to 6, and this time I have x squared dx. This has to equal my f of c, which in this case will be c squared. So we go through and solve this. We end up with 1/6, and then here when we integrate, we'll have 1/3 x cubed on the bounds from 0 to 6. This equals c squared, and here we end up with 1/18. 6 to the 3rd is 2/16, so 1/18 times 2/16, which means 2/16 divided by 18 gives me 12, which is what my c squared is going to be. So now this problem ends up being just slightly different because we solve for c, we get plus or minus the square root of 12, which is plus or minus 2√3 when I simplify this. But look at the bounds. The bounds are 0 to 6. So this, we have two answers, negative 2√3 and positive 2√3. Oops, 2√3. And since I'm going from 0 to 6, I cannot use this one. So this is my only answer. C has to be 2√3 because negative 2√3 is not in my bounds. All right, let's move on to number 3. On number 3, we have to find the volume of a solid obtained by revolving about the x-axis, the region bounded by the graphs y equals x squared plus 4, the x-axis, the y-axis, and the line x equals 3. So let's go ahead and first start by graphing what we've got going on here. So I'm going to draw a quick sketch, and I have the graph of x squared plus 4, so it's going to come up here at 4, and it's going to be a parabola. And the region bounded by that, the line x equals 3, 1, 2, 3. So at 3, we end up like this. And the x-axis and the y-axis. So it's this region in here that we're going to rotate, and we're going to revolve this about the x-axis in this manner. So using what we've learned, we want to take our slices to be perpendicular to the axis of rotation. We are going to go ahead and use a disc method here, and I don't need washers. This is straight discs because we have our equation, and there's no two bounds, there's no second equation, there's only one, and I'm going to rotate this. So these are perpendicular to the axis of rotation, So these widths of my rectangles will be dx. We know the volume is the integral of the area, and in this case, my dx's, my slices are going to go from 0 all the way to 3, from 0 to 3. So this will be pi, because remember, it's pi r squared h, because these are cylindrical shells, and we are, well, not shell, I should be careful not to say shells, but these are cylinders, and this height, this width, is what we're going to call our dx, and our radius will be that value from there to there. That'll be our r, and my dx's are actually my widths. So we end up with pi, I'm going to put the pi on the outside, from 0 to 3, and in this case, my radius is this x squared plus 4, that's the length here that I'm dealing with. So from here to here, that's my radius. I'm going around the x from 0 to 3. My slices get sliced up this way, perpendicular to my axis of rotation, so they're going from 0 to 3. Go ahead and complete this with our dx, which is those little widths, and we end up with pi from 0 to 3. I forgot the squared because it's r squared. Don't forget that. It's important. And now I'm going to go ahead and FOIL this out. So this ends up being x to the 4th plus 8x squared plus 16 when I FOIL that out dx. So I've multiplied that through. Now let's go ahead and integrate, and when we integrate we get pi. This will be 1/5 x to the 5th plus 8/3 x cubed plus 16x on the bounds from 0 to 3, which ends up being 843 over 5 pi, and then this will be units cubed. So you could double check that when you put in the 3. You get 3 to the 5th, 1 over that over 5, 3 cubed, 27 over minus 0. The rest of it will be 0. So plug that in, work that out. It should be 843 over 5 pi. Okay, moving on to number 4. Number 4 says, find the volume of solid bounded by y equals x to the 3rd, x squared, and the x-axis revolved about the line x equals 2. So this one is going to end up being a little bit more difficult here. Let's see if we can graph what we've got going on. So I'm going to have x to the 3rd, so this ends up being, comes up, down from down here, and we'll go up through here. X equals 2, so we've got 1 and 2 right there, so that'll put us at a height of 8 just by simply plugging in into x cubed. And the line x equals 2, and we're going to take this and we're going to revolve this about the x-axis about the line x equals 2. So we've got this bounded here, so it's this region in here, and we're going to revolve it about this line right here. Let's put that in another color so we can see that, and it's this line right here in red. We're just taking this whole thing and we're going this way. Alright, this kind of is a little tricky. If you were to set this up using a simple disk method, because we've got only one equation, we're going to revolve it, but we're going to shift our line of rotation. Now remember, we're revolving, so we need our slices perpendicular to the axis of rotation. So our slices need to be this way. So I'm dealing with dy's if I take these slices perpendicular to my axis of rotation, or my line of rotation in this case. So I need dy's. So solving this in terms of y, I'd get the cube root of x, or the cube root of y equals my x. So we've got that. Now, we are off the axes. We're off the axes, which is right here, by 2. So we're shifted by 2. So we're going to take this minus our line of rotation in this case. So if I set this up through simple shells method, we've got the volume equals the integral of the area, and in this case it's going to be pi, and since we're going dy's, we're going to slice it from 0 to 8, and we've got the cube root of y. Now it would be dy if we're just going around the y-axis in this case, but we're not. We're shifted off by 2, so we're going to say minus 2, and we are going to go ahead, square this, and dy. Now there are a couple other different ways to do this. If you set this up actually as 2 minus cube root of y, the other way around, which could make sense to you, and does, you'll end up with the square terms, it squares itself out, so you won't get that negative. But this is using the a simple disk method. This is how you would set this up. And this is kind of crazy to integrate, believe it or not, because squaring this term out is pretty intense. If you square this term out, you're going to get, let's see, you're going to get the cube root of y squared, so you'll end up with y to the 2/3, and then you'll end up with this as being minus 4y to the 1/3, and then we'll end up with plus 4 if you square all this out. And then at that point you need to integrate, and when you integrate you'll end up with 3/5 y to the 5/3 minus 3y to the 4/3 plus 4y on the bounds from 0 to 8. Plugging all the values, and this is where it gets intense. But when you plug in the 8, it actually works out pretty good, because 8 to the 5/3 would be the cube root of 8, which is 2. You square that, 32. So you end up with, we got a pi on the outside here, so you end up with pi times 30 times, this will be 3/5 times 32, and then you end up with minus 3 times 16 plus the 32. And solving all this and working all this out, you'll get 16. This equals 16 pi over 5 cubic units. All right, now that's one way. Another way you could set this up is you could do this by shells. And let's take a look at what we have if we end up doing it by shells. So I've got this situation going on here. This time I'm going this way, so I need to be parallel. With shells, I need to be parallel to the line of rotation. So I'm taking my slices as dx, so that doesn't change. And we say with shells, we've got a different formula. We'll end up with 2 pi, and now my slices go from 0 to 2. So 0 to 2, and then remember with shells, we have 2 pi on the bounds from a to b of x times your f of x dx. And in this case, we've got x, but we've got 2 minus x because we're shifted off by 2, because that's my line of rotation. 2 minus x, and then this f of x is just x cubed dx. This is much easier to work out and integrate, because here you're going to distribute this. You get 2x cubed minus x to the 4th. Again, much easier to integrate on these bounds, and you end up with the same answer in the end as 16 pi over 5 cubic units. So in this case, this would be probably more preferable to use, because this right here, right in here, let me get my pointer tool, this right in here is kind of nasty. All right, let's move on to number 5. In number 5, we have to find the volume of solid that results when the region bounded by y equals, this is a square root of x, y equals 2x minus 1, y equals 0, and x equals 0 revolved around the y-axis. So let's take a look at what we've got here by graphing it. So graphing this is what we're dealing with. We've got this square root of x function goes like that, and we've got 2x minus 1, so it crosses down here and then comes up, and we don't care about this region down in here because we are bounded by x equals 0 right here and y equals 0. I'm not sure why it would say x equals 0 in our problem. We don't really need that. Since we've got y equals 0, we're looking at that region right in there. So this is what we're looking at, this region bounded right like this. So x equals 0, y equals 0, but the y equals 0 kind of takes precedence over that. So we're going to go ahead and just say that it's in this region in here based on what we're given. And then we're going to go ahead and take this, and we are going to revolve this about the y-axis. So this whole thing is going around in that manner. All right, so since we're going about the y-axis, we need our slices to be perpendicular to our axis of rotation, so they're going to look like that, so we end up with dy's. Now here we've got two equations, so we're going to have an outer radius, which is our r, and then we're going to have an inner radius, which is that one. So we take the big one, rotate it around, so this larger one is going to get rotated around. Then how do we hollow it out? We take this little one and subtract it out. So we are going to use a washer method in this one. And since my slices are dy, I need to solve each of these. So I end up here with y squared equals x. And here I'm going to end up with y plus 1 over 2 equals x. I need to know where these cross. You could have set them equal to each other at this point right here. So the square root of x equals 2x minus 1. You solve this and you are going to get, since we're starting bounded down here, we're going to go from 0, and this point that'll cross up will be 1, because here you'll get x equals 1. And again, we're going to go from 0 right here all the way up to 1 in our slices. So we end up with the volume equaling pi times the integral from 0 to 1 in our y's. And we've got big R squared minus little r squared dy in this case. So the volume equals pi times 0 to 1 times the integral from 0 to 1. And this will end up being the larger one is going to be this y plus 1 over 2 squared, that's my larger radius, minus my smaller radius ends up being y squared, and we square that, and we're going to put our dy there. Those are our widths. Alright, let's go ahead and finish this problem out. So we're going to end up pi times the integral from 0 to 1, and this, when we FOIL everything out here, we'll end up with, let's go ahead and, we can write this as 1/4, and then we'll say this is y squared plus 2y plus 1 minus y to the 4th. Did a little trick there and took out that 1/4. And this ends up being pi from 0 to 1, and foiling this, combining like terms, you end up with negative y to the 4th. Actually, you don't have to FOIL, you just have to distribute the 1/4. 1/4 y squared plus 1/2 y plus 1/4, and this will be dy. Alright, let's go ahead and integrate this. We end up with pi times negative 1/5 y to the 5th. We're going to move this up. Negative 1/5 y to the 5th plus 1/12 y to the 3rd plus 1/4 y squared plus 1/4 y on the bounds from 0 to 1, and plugging this in, you get pi, you get negative 1/5 plus 1/12 plus 1/4 plus 1/4. All this ends up being, in the end, 23/60 pi cubic units. Okay, moving on to number 6. In number 6, it says, Ben is about to haul up a 32-meter length of rope hanging from the top of a building, which is 32 meters above the ground. Also, how much work will it take to haul up the rope if it weighs 1.8 newtons per meter? Assume uniform weight. So let's draw what's happening here. We've got this guy up here, and a rope's hanging down. This whole rope is 32 meters because it's 32-meter building. So yes, it's not drawn to scale, kids. I understand. All right, so now taking a look at this situation. First, let's find what the total weight of the rope is going to be. And here we end up with 32 meters times 1.8 newtons per meter. And this comes out to be 57.6 newtons. And we need an equation for the weight loss, because as you pull the rope up here, as it's going up, there's more of it hanging here, so there's less weight that you're pulling up. So there's going to be a weight loss as it's coming up. Well, we start with the total weight, 1.56, and we're going to lose 1.8 per meter. So that's our basic equation. So the amount of work done will be the integral of the force, so this is our force equation. And this will happen from 0 to 32, and it'll be 57.6 minus 1.8x dx, don't forget that x. Putting this in our calculators, we end up with 921.6 Newton meters, which is a joule, and that's how much work it's going to take. All right, moving on to number 7. Suppose we've got f of x equals x e to the x and g of x equals sine x plus 1. We need to find the area of the region in the first quadrant bounded by these graphs and x equals 0. So what we are looking at here is this situation. We've got a graph. If we graph e to the x times e to the x, and that will end up looking something like this. It does cross through 0, so this is x e to the x. And then the other one, sine x plus 1, it starts, it'll come kind of like this through there. This is the sine x plus 1. So you can use your graphing calculator to help you do that. In fact, you do need your graphing calculator on this because we have to find this point of intersection. And this point of intersection, I will tell you, comes out to be 0.78054. Again, graph with your calculator and find that point of intersection. So graph each of those, find that point of intersection. All right, so now we want to find the area. So the area is just simply the top curve minus the bottom curve. So in this case, the area is going to be the integral, and so we need to go from this point to 0.78, from 0 to 0.78054 of the top curve. In this case, it's sine x plus 1 minus the bottom curve, which is x e to the x dx. This is a calculator problem. You will need to use your calculator to integrate this. And when you put this in, integrate it, you end up with 0.54901 square units as that area. All right, for part B, the volume when we rotate it about the x-axis. So we're going to take this region and we're going like that around this x-axis. So we need to find that volume when we go about the x-axis. Let's go ahead and choose a little darker color here. Okay, so this ends up being the integral of the area, and in this case we have pi times our slices are perpendicular to our axis of rotation, so we've got dx's here, and we're going from 0 to that 0.780 to the 0.78054 value, and we've got sine x plus 1. That one we're going to rotate around, right? And then we're going to subtract this one. So this minus this. So we need a washer method here. So this is sine x plus 1 squared minus our x e to the x squared dx. Now this might be a challenge putting it into your calculators. If you have the new TI software, it's a lot easier. If you have the older one, be careful. Make sure you use enough parentheses so that you don't leave anything out of this. And we use our calculators, we integrate this, the volume ends up being 0.96679 pi cubic units. All right, moving on to part C. Let's move this up and take a look here. And in part C, we are given that the region in part A is the base of a solid. For this solid, the cross sections perpendicular to the x-axes are squares with bases extending from f of x to g of x. Find the volume of the solid. So basically, here's what we got. Let's draw this out again. So we've got this curve, then we've got the top part here, and then our bases here. These are squares that come straight out of the paper at you. Okay, so these are coming straight out at you. These slices are going to be squares, again, coming out of the board at you, out of the paper at you. All right, so the volume is the integral of the area. In this case, the area I'm dealing with is a square, so side squared. And what's the length of the side? Well, that's the length of the side right here. This top curve minus the bottom curve is the length of my side. So I end up with my S as being sine x plus 1 minus my x e to the x. and I'm going to square this. Let's go ahead and leave it like that, and we'll just square it when we put it in our formula. So the volume is the integral to area, which in this case is side squared, and this ends up being, remember there's no pi on this, we're not rotating, so there's no pi. So 0 to, yes, I know you like to eat pi, 0.78054 of sine x plus 1 minus x e to the x. This is my side squared dx. Again, calculator problem. We plug this into our calculator. We get this volume as being 0.45159 cubic units. All right, moving on to number 8. In number 8, we have to find the area between y equals 2 cosine x and y equals cosine x. Probably should have, to be consistent, I put a parentheses there. Could have put a parentheses on this as well right here. Okay, so setting this up, again, let's go ahead and graph our situation and see what we're looking at. I graph this, and I've got two curves here. The top curve is going to look like this. This is the 2 cosine x, and we're going out to pi over 2. It will cross through pi over 2 right here. And then we've got our cosine x that starts up, comes down, and it does go through pi over 2 as well. So this one is cosine x. So since we need to find the area between curves, I just need the top curve minus the bottom curve all over the bounds from 0 to pi over 2. So this comes out to be the area equals the integral from 0 to pi over 2 of the top curve 2 cosine x minus the bottom curve, which is cosine x, dx. Now you can do this with your without a calculator. This is an easier problem. Integrating, you'll get 2 sine x minus sine x on the bounds from 0 to pi over 2. Plugging these in, 2 sine of pi over 2 minus sine of pi over 2 minus 0 when you plug in 0, because sine of 0 will be 0. So you end up here with 2 minus 1 minus the 0, so it ends up being 1 as your area. That's going to be square units. All right, last problem here, number 9. And in number 9, it says, Ravine Industries, a manufacturer of cookies, stores its cases of cookies in an air-conditioned warehouse for shipment every 14 days. RVR, the owner, tries to keep 600 cases on reserve to meet occasional peaks in demand, so a typical 14-day inventory function can be expressed as what we have plus our 600T on the interval from 0 to 14, which is our days. Find RVR's average daily inventory for the 14-day period. Well, this is just an average value problem. So we've got an average daily inventory is what we're finding. So we need to take the average value of our I of t function. So in this case, we end up with 1 over 14 minus 0, 14-day period, on the integral from times the integral 0 to 14 of 600 plus 600t dt. So working this out, this one's pretty easy to integrate. We end up with 600t plus 300t squared, 1 over 14 times this on the bounds from 0 to 14. And plugging it in, we get 1/14 times 8,400 plus 58,800, sorry. And we work this out, we end up with 4,800 cases as our average. All right, I hope this review helped, and good luck studying for your test, and good luck on your test.